Okay, ladies and gentlemen, welcome back. I wanted to use this time to tie up a couple of loose ends from the previous video about electric fields, and then spend some time solving problems, since that's officially the first topic that we didn't have time solving problems together in class, okay? So let's tie up some loose ends on electric fields. Okay. First and foremost, let me remind you, electric fields are the things that we say are responsible for the electric field lines, right? Positive charges, they emanate outwards. Negative charges, the lines emanate inwards. And again, we said, what was the difference between an electric force and an electric field? The electric field, right, is a one-player system, right? It talks about what is the field that one particle puts out, such that if you were to place another particle next to it, how would you feel its effect? Whereas force, right, was the two-player system, right? That's the system where you talk about the electric force of one particle acting on another. We need two players to play this one, and this one we only need one. That gives us right away then the formula for the electric field, right? It's going to be K, Q, over R squared, right? Whereas the electric field required two charges, Q1, Q2, over R squared. Same rules apply, opposites attract, like charges repel, etc., right? And so the easy way that we know that if we have one of these, we have the other, is that if you take a look at this one and compare it to this one, the electric field is nothing more than the electric force divided by one of the charges, okay? And so really, if we have one, we have the other, and so depending on how a problem is stated, we might have one versus the other and use it to find the other one. As far as the units, right, nothing special here, right? Electric field, if it's force divided by charge, then the unit is just Newton per Coulomb, which I remind you is Newton versus Coulomb. Great. We don't give that any special name. And what are the typical electric field sizes that we'll see? Probably about 10 to the 5th, 10 to the 6th, okay? 10 to the 4, also good. So if you get answers around that range, we're typically sitting pretty good. Okay. That's the electric field. These manifestations up here are the electric field for a single point charge, okay? But sometimes we know that macroscopic objects, or what's our word for macroscopic objects in physics, right? These are our rigid bodies. Sometimes these have their own electric field that they're going to put out. Or if we're talking about, if we had a bunch of charge on like a dime, right? And then we put, it therefore had an electric field, and we said, what's its influence on an electron, let's say, right? The dime is enormous compared to the electron, right? So we have to be able to talk about electric fields of continuous media or of rigid bodies. Now, the lucky thing for you guys is kind of like when we talked about how I couldn't expect you in a non-calculus-based physics class to calculate a moment of inertia, right? The same thing goes here. I can't expect you to calculate a pure electric field of a rigid body without knowing some calculus, right? So we're just going to jump straight to the answer, right? For a rigid body of some shape, right? Again, this is kind of like our moment of inertia, how we couldn't derive those formulas, right? E is going to be given as sigma divided by epsilon 0 times A. Now let's make sure that we know what these things are. Epsilon 0 we've already seen before in class together, right? This was our different way of writing the electrostatic constant K, which I remind you is 8.8 times 10 to the negative 12th coulombs squared per Newton meters squared. Okay, remember that was called the permittivity of free space. Sigma, right, since this is now a rigid body, sigma is a charge per area, right? Namely, it's a density, if you will, of how the charge is spread over the body. And this is typically, for our cases, again, in a non-calculus-based class, a constant that you're either given or you're asked to solve for, and A is the area of the body. So what this means is that if you have some shape with some area, right, the charges spread out over the area, and how they're distributed we call sigma, and that sigma is what results in some electric field. But we can see that this is a very straightforward formula. So what it means for us is that there's only two ways that we'll ever be using electric field formulas. It's either this one right here for rigid body or one of these for a singular point charge. Okie dokie. Let's jump into using those to make sure that we're all on the same page. Let's go with the one that we just talked about, this idea of finding the electric field as being sigma over epsilon 0 times A, right? Namely, when we have something that is of continuous media. I like this problem because it's a nice real-world example, right? A lot of us have air filters either in our car or in our home, right? These ionized air filters. Why is that important? Because what does it do? Air gets ionized or charged as it passes through the filter, right? The filter has a low-grade electric field in it, which then forces the particles to move one way or another because like charges repel, opposites attract, okay? And you can then manipulate how the air goes, pull out some particulates, and then the clean air exits the other side. And that can be seen in this picture here. So now what's important about this picture here? They give us some information about this air filter. There are two plates, the one in the greenish color here and the one in this Advil color here, right? And what do we see? We see that each one of those plates, they're separated by some distance, but more importantly, each one of those plates has a certain length and a certain width, which means that for these plates, we definitely know the area. It's the length times the width. With one caveat that we got to make sure that we convert these centimeters have to go to meters, right? Because centimeters, like always, is a very, very bad unit. Further, we're seeing that each plate is charged to a constant, sounding familiar, right? That this is going to be how our charge is spread out. Sigma, we could have just as well called it Q, but we'll call it sigma just to delineate the fact that it's spread across an area. So in reality, if we're going to use this formula, putting a check mark next to what we know and underlining what we don't, we know sigma, we know epsilon naught, we know A, right? Check that out. That's going to be my new color that I never use in class, yellow, right? I got really excited about that. You probably didn't, but I did. So we got yellow here. We got a check mark next to everything that we want. So this one really is back to just a pure plug and chug, right? Our E is going to be our 540 nanocoulombs, whole thing divided by epsilon 0, which again, I remind you, is our 8.8 times 10 to the minus 12 coulombs squared divided by newtons meters squared. Whole thing times the area, which again must be each one of those lengths and widths must be converted to meters. So this is in reality a 38 centimeter is 0.38 meters times 0.206 meters. Okay? And then we just have to figure out what happens to the units because the rest of this is plug and chug. Let's take a look at it to make sure that we get the units right. What do we expect for the units of an electric field? Right? We're going to expect some number times newtons per coulomb. Let's hope that we get that. When we take a look at this, meter times meter is meters squared, but those meters squared kill the meter squared here. Coulombs in the numerator kills 1 coulomb in the denominator, leaving 1 coulomb in the denominator. Newtons is in the denominator of a denominator, which means it's going to get moved upstairs. And what do you know? The world is a happy place. We get newtons per coulomb. The rest, boop, 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 bop, we plug it into our calculator. And with my level of rounding, I get 7.8 times 10 to the 5 newtons per coulomb. And if we look at that value, again, that's right around the number that we said would be numbers that we're used to looking at. Okay? So really, when we use this formula, when we're faced with a problem that has this formula, they're going to be as simple as this, right? We're either given the electric field and you got to find A, or you got to find sigma. But I can't make it any harder than this, because much like moments of inertia, you can't calculate this stuff without calculus. What is the only other things that can come up in this type of problem as a caveat, right, is that here we had a square. And so we know the area is the length times the width, right? I could change this problem around and say that the plates of this thing were circles, right? In which case we know the area of the circle is pi r squared, and so there I'd have to give you the radius. Whatever the shape may be, okay, this is how we're going to do it, okay? So again, make sure that as long as we know our formulas for areas, there's nothing more to this. Okay, but by this point now, we've done some practice with electric force in class, and again, I remind you that's jumping back over here, right? Looking at our overview of the notes, or at least of the top part of the notes, right? We've already said that if we can figure out electric force, we can figure out electric field then by just dividing by the charge. So really knowing one is enough to know both. So, like we typically do in class, I want to show us a problem that shows us how deep this rabbit hole can go, and make sure that we do one that drives home the fact that we can never forget the old stuff, because there's always a way to work it in, right? Because in reality, although this is a new type of force, an electric force, remember, it's just a force, which means it relates to Newton's laws, which means it relates to everything else that we've done in class. So here we go. This problem might not have much nostalgic reference to you as it does for me, but gosh, when I was growing up, we didn't have all these flat screen TVs now that are huge, 60 inches, etc. No, the biggest TV that we had when I was younger was a 30-inch TV. And that 30-inch TV was built into a cabinet, and your whole TV was a piece of furniture that sat there. You can probably still look up a picture of these on the internet. Totally crazy. And 30 inches was considered to be enormous. I remember my father saving up $1,500 to get one of these cabinet 30-inch TVs. So, I bring that up is because the TVs were so gigantic because they had inside of it what was called a CRT tube, which stood for cathode ray tube. Okay, and what these cathode ray tubes were, okay, they were a plate, like I'm drawing to here, of negative charge with a plate of positive charge, separated by a certain distance. And what would happen is that when you turn the TV on, it would turn on an electric field. Obviously, electric field moves from the plus to the minus. Opposite charges attract. And what would happen is it would kick out electrons from the negative plate that started on the negative plate. So they started with an initial velocity of 0, right? They are attracted to the positive side of the plate because opposite charges attract. And they would end up outside of this plate after being fired through a hole with some final velocity. Then we would construct the same type of thing, two plates with another electric field between them, okay? And then we would flip the entire system so that it went like this, and what would happen is the electron again would be attracted towards the top plate and thus deflect its path, okay? So we had the gun piece and the deflector piece. And eventually then what would happen would be is that electron would come over here, bam, and smash onto the screen, and then here is young James O'Brien out here eating a bucket of popcorn. And I have an awesome cape. There's me outside enjoying the millions of electrons that are slamming into the screen every second. And so how could you change where it slams on the screen? You would change it by varying the electric field here, because a different field would produce a different force which again, I'm just going to take some of these off now, that different field would produce a different force, which would lead to a different deflection path, maybe one with a lesser field that then looks like this, and the angle would change. Okay, that's what we want to talk about in this problem. Okay, so that's the trip down memory lane for why I think this problem is cool. Okay, but for our purposes, how do we solve it? Let's see what we're given. The first part just walks you through what I just talked about, okay? But the important part here is that we are given all of these different lengths, okay? And we're also given the initial velocity and the final velocity of the electrons after it passes through the electron gun phase. So let's call that the gun phase, okay? They want us to find in the gun phase the electric field E. Now, at this point, we know there's two ways to find electric field, right? There's the electric field is sigma over epsilon naught A, and then there's the electric field is equal to the electric force divided by charge. And which one are we going to use? Well, it looks to me like this one right here is going to be a bad idea. Although we are given the separation distance, we're not given any other information that would imply what the area of these plates are. If that's the case, then we're going to have to use the old one, which tells us that if we really knew how to find force, then we would be able to find the field. Okay. Well, how can we do that? What else do we know about the gun phase? We know that the initial velocity of the electrons is 0. We know the final velocity of the electrons are given as 6.0 times 10 to the 7th meters per second. Yeah, a really fast speed, but that's what we would expect. They're tiny little electrons, right? Well, how far do they also go? They also go a delta x of 0.04 meters, right? Because centimeters is a bad unit. My goodness, we're given an initial velocity, we're given a final velocity, we're given a change in x. This sounds a whole lot like some of the first things that we did together. So what's our strategy going to be here? We want electric field. We could get electric field if we had electric force. But all forces, no matter what they are always ma by Newton's laws. So another way of saying that is that we can get E if we had F. We can get F if we have A. And how do we get A? We can get A by our good old kinematics, right? Because look at all this wonderful stuff that we're given here. So let's do it. Remember equation 5? That one says that V final squared is equal to V initial squared plus 2A delta x. Put a check mark next to what we know and underline what we don't. This one only has one unknown, so we can solve this right away for the acceleration. Man, I really like that yellow, but I don't know how it's going to come out on the screen, so I'm gonna not use it. Okay, we solve this for the acceleration then, and that's going to be V final squared of, again, this is V final with respect to the gun phase, divided by twice delta x, where I've already now converted delta x into meters. We plug this in, and what we see is that we get an acceleration of 4.5 times 10 to the 16 meters per second squared. Yeah, a tremendous number. Once we have that, then we can use the acceleration to find F, because F equals ma, and we know what the mass of the electron is because, like we said in class, that's always a given. You can find it in the front cover of your textbook or the internet. It's 9 times 10 to the minus 31 kilograms, super small, which therefore results in a force of this number times this number, which, yeah, is still an outrageously small force. But that outrageously small force in order to get that outrageously small force, we now want to know finally what is the electric field that generates that very small force. Well, that's going to be the force divided by the charge. The charge of the electron is also known, right? That's our charge E. And so when we plug this in, we see that the electric field is going to be 2.5 times 10 to the 5th newtons per coulomb. And we have it. Again, we wanted something new, electric field, and it required us to go all the way back to what we had in the first semester in order to solve this. Now, for part B, the steering field, now this is talking about the deflector phase. And so I'll do this over here. I'll zoom in a little bit. Now, in the deflector phase, we know that now the electron is undergoing two-dimensional motion, right? It has a v initial in the x and it has a v initial in the y. Its v initial in the x is exactly the number that they told us before, right? It's the final velocity of the gun phase. And the final velocity of the gun phase was the 6.0 times 10 to the 7. The initial velocity in the y direction is 0 because it comes out moving only in the x direction. Okay? So, if we want the angle, again, we have to think of there's not many strategies that we have to get angle. This is not circular motion, right? But what do we know? We do know that when that thing finally gets to the end, it's going to have a final velocity which looks something like that, which really comprises of a v final in the x and a v final in the y with an angle right there. So, if we find the v final in the x and the v final in the y, then we can use them to find the angle, because the angle will be, as always, the inverse tangent of the y piece over the x piece. Good, so that's the strategy. Let's hit the low-hanging fruit first. Which direction is the force happening in the deflector phase? Well, they show it to you right there. The force is going up, namely only in the y direction, which means that the v initial in the x is the same as the v final in the x, because Newton's second law tells us that an object remains in that motion unless acted upon by an external force, and here there's none. So, we already got that piece. Now, if we only knew v final y, then we'd be ready to rock and roll. Okay? Well, what is producing the force? The electric field is producing the force. Okay? And they tell us in part B that that electric field has a 1.5 times 10 to the 5th Newton per coulomb over that region, which means we can use the electric field to find the electric force that these electrons feel. And then if we knew the electric force, we can find the acceleration. And if we know the acceleration, then we can get v final in the y. Namely, it's almost the exact backwards as to what we did last time. Okay, let's finish the job then. Let's finish the job. So, if we dive right in, we know then that we can use that electric field to find the electric force, which would be the electric field times the charge. And again here, remember that charge is the charge of the electron. So plugging in those numbers would give us a value for the force, but we might as well take this one step further, because if force is equal to ma, then we know that A, which is what we wanted from this, is going to be E times the electric field divided by the mass of that electron. Again, mass of the electron and charge of the electron are numbers that are constant. We plug these in and we get a 2.6 times 10 to the 16 meters per second squared. Again, a tremendous value. Now that we have the acceleration, we can then use this to find the final velocity in the y. We know the initial velocity in the y direction is 0. So that gives us enough information, because if you look over here too, we also know the length of this guy, right? Sorry, there it is. The length is 0.05 meters. And so we can use the x motion to know how long it took that guy to get across the plate, because we know that by equation 4, x final is x initial plus v initial in the x times t plus 1/2 acceleration in the x t squared. But this piece goes away because we're not accelerating at all in the x direction. X final minus x initial is the length. And so the time then can be solved for by being the length divided by v initial in the x. And of course, this is going to come out to be a horrendously small time. 8.3 times 10 to the minus 10 seconds. Again, that's using v initial in the x as given. The 6.0 times 10 to the 7. And once we have the time, now we can plug that in to the same exact type of equation, namely equation 3, right, which says that v final in the y is v initial in the y plus a times t. Time, again, is the link in our two-dimensional motion. We know it. A, we know. V initial in the y, we know. So we can finally get v final in the y, which is going to be 2.2 times 10 to the 7th meters per second. Once we have v final in the y, we then can go back to our strategy, which says find the angle by taking the inverse tangent of the y component divided by the x component. And again, just plugging in numbers for reference here, that's going to be our 2.2 times 10 to the 7. This is going to be our 6 times 10 to the 7. And getting that into our calculator gives us an angle of about 20 degrees. And there we have it, ladies and gentlemen. Nothing outrageously difficult about that problem, except once again, it makes us go all the way back to where we started, thus drawing upon the point that, yeah, this stuff snowballs. We can never, ever let any of it escape our mind. But that's why we take good notes, and that's why we have these videos. Ladies and gentlemen, I will see you this week virtually in class. And until then, never stop thinking.